Welcome back. Let's call this President Garfield's Pythagorean Theorem's proof. This proof is credited to President Garfield. So let's get started. This is a standard 8.5 by 11 sheet. Excuse that out of focus. And we need to get a square out of it. So let's fold and cut our square. Let's go like that. Let's cut the excess. Gently we cut. Let's open our square. We should have a nice diagonal. Now let's fold it in half. We have to construct some lines for ourselves in order to demonstrate the theorem. We're going to give it a geometric explanation. Now fold your paper as I'm folding. Now we folded it into 4 parts. Now at perpendicular we fold it into fourths again. There we go. There we go. Now we should have, or we have, as you can hope to see, a sheet that's 4 by 4. Now we're not quite done yet. We need to add some marks to help us visualize what we're going to do. And for that, we need to draw some lines, but in a very specific way. Notice that it's going from edge to edge, and we'll continue that pattern, edge to edge, edge to edge, edge to edge. Now we can label these. This is the hypotenuse of this triangle. This would be C. This would be A. And this would be B. This refers to we're labeling the sides of this triangle. Its leg is A, the other leg is B, and its hypotenuse is C. Alright, now I'm going to cut off, remove one of these, actually 2 of these triangles. And I'm removing them mostly because it's easier to fold and control what I'm about to do. Now what I'm going to do is I'm going to fold really this this vertex, this point, and put it on top of that one, which is just simply as doing that. Okay. And again, I want to emphasize that this is C. Alright, just as a reminder, if you recall, let's go back to the sheet here, that the formula for the Pythagorean theorem says this: a squared plus b squared equals c squared. And these correspond. This is the a, that's the b, and that's the c. Alright? So what I want to do now is to actually add or connect the algebra and find that, or show you or demonstrate algebraically that indeed that the sum of the square of b plus the square of a does indeed equal the square of c. So that's in the next part. In this part of the project, or this demonstration I should say, I want to emphasize that what we folded is really a trapezoid. And to emphasize that it is a trapezoid, I've cut out a trapezoid like that, so that when we take the area of the trapezoid, there's a familiar formula which I hope that you will recognize, which is to say that we have b, we have to take the average of the two sides, b plus a, take their average, that's one side, times the other side, which is, we'll call it b plus a. Even though this is in reverse, I want to keep it consistent with what I have. Okay, now we want this to be equal to the following. This is an area, the left side is an area, and the right side also has to be an area. Now we have two triangles, so we have 2 times the area of a triangle, in this particular case is AB over 2, and there's 2 of them, plus half of a square, which turns out to be c squared divided by 2. Now, let's see. To simplify this expression, I'm going to multiply both sides by 2. But before I do that, I notice that I can cancel these 2's. And so I'm going to multiply both sides by 2. So here, when I multiply, I get b plus a times b plus a, which is just b plus a squared. On the other side, I'm going to multiply 2 times ab, which that's what it is, 2 times ab plus 2 times c squared over 2. The 2's cancel, and so I get c squared like that. So let's expand this left side, and we'll get, well, I'm going to put it in order now. We should get the a first, so that's going to be a squared plus 2ab plus b squared. And that's going to equal to 2ab plus c squared. Now we notice that 2ab is common to both sides, so we can just delete common terms. So now we're left with a squared plus b squared equals c squared, and that's it. That's the formula. That's the Pythagorean theorem. Now, whether President Garfield took these steps, I cannot say, but these are the steps that certainly lead us to the formula. Okay. In the next step, I'm going to actually show you or demonstrate how you can do this, actually show it or demonstrate it by cutting paper. In this part, I'm going to show you how you can actually demonstrate that the theorem is indeed true. So let's go back to our original square. We've marked it the way we did it in the other parts of the video, but we're going to now cut off. Notice that this square is indeed the square of C, which is the hypotenuse of the triangle. Because that's what the theorem says, that the hypotenuse, the square of the hypotenuse, is equal to the sum of the square of the two legs. So first of all, let's just get the hypotenuse. Let's separate that. So we have only the square of the hypotenuse. One more. There we are. Now we have the square of the hypotenuse. Now this diagram shows that now I'm using the square of one of the legs, which is B. This large square is the square of B, and this little square is the square of A. And so I'm going to show you how you can combine those two and literally reconstruct C. So I'm going to cut off, I'm going to cut away the parts that are irrelevant. In other words, I'm only going to leave excuse that little sliver there. I'm only going to leave B squared and A squared. There we go. Let's put those away. And I will remind you that this is A squared and this is B squared. Now, if we take a line from that vertex to this vertex over here, we can draw it. Actually, we can't draw it completely. Now we take and fold it across like that because we want to find the midpoint, and it's perpendicular. Alright, notice that the perpendicular intersects the bottom right there. Okay, now the idea is that how this works is that we're going to, first of all, we draw a line here just to emphasize, to show what we're going to do. Now you can probably tell that this is the hypotenuse of C, but right now we're going to wind up with a rather uncomfortable shape. But that shape really is, this construction I'm going through is really one way to sum or get the sum of the squares of A and B and do it mechanically or geometrically. So I'm going to cut this part off here, and I'm going to paste it there. I'm going to use some tape like so, and allow another piece of tape just to make it more secure. Put it there. Now I'm going to cut along this diagonal. Like so. I better put another piece of tape right there to make it more stable. And now I can put this over here. And that, I think you begin to see that indeed that the two squares, or some of the two squares, not quite done yet. Now this is the sum of the two squares, and this is C. And you can see they are the same. We can fold them in half like this, the way we did it in the video, and we can check ourselves to see if that is also true. Because halves of equal squares should be equal to each other, or should be congruent to each other. So here's half, and there we go. They are the same, they are congruent. And that supports the theorem. Thank you, that's the end.